And I will start with a short introduction. As it was said, I'm working as a big data engineer at Allegro. I'm also conducting some big data trainings, and I have a data science flavor. So I was always kind of high in maths, and I kind of love it. So it was natural kind of flavor for me. The most important question before starting any kind of project is to answer why are you doing it? What is the purpose? What are your problems? What kind of problems do you want to solve? And, well, let's think about the data for a moment. What are the three most valuable assets of your company, if you were to tell? Who amongst you think that people is the most valuable asset of your company? Who think that data should be at the top 3 places? And answer yourself, could you live without your application working on production? Probably yes. But could you live without losing data from production? Probably no. So they are quite important, and they should be the first-class citizen in your company. And it is nowadays, it is a standard that applications are being monitored. When your application on production goes down, you are being notified, and business does not go to you and say, okay, your app is down, you should try to fix it. You know it before them. But with data, it is not so good yet at the moment at many companies. So we had the issue with it, and we wanted to solve it. So that's why we were interested in anomaly detection. That's the background of this project. But last but not least, this is a nice quote. In 20th century, engineers built, for example, houses, bridges, and if the wall in a house was 89 degrees, 88, it was the mistake. But in 21st century's IT engineers they have huge power, and they made huge mistakes, like, for example, with the GitLab production DB being erased. Those mistakes are very costly, and you should be the first one to know that you have made it. Okay, it's working. So, our goals. First of all, we want to know that the data is being lost from the clickstream. We gather the data from the user experience, the behavioral kind of data, and if they are going to get lost, you can think of it like losing money, because you won't serve good recommendations, you won't fit your ads to the current user, so you can reason a little bit about it. And if you do not know what's the typical statistical volume of data that you gather from the clickstream at the current box showed in the web page, then you cannot know how to improve it, if it's getting better or getting worse. And, if something is getting better, it might be an anomaly. If something is getting worse, also. So, last but not least, it should be a monitoring system, so that if something goes down or it's behaving somewhat unusual, the team that is being responsible for this kind of project, because our main page is divided into multiple projects, should be notified that something is going on at the moment. Sorry, I'm having some issues with it. Okay, so main questions before starting. From where should we get the data? How fast shall we react? Do we have to really react in real time? Or is there some kind of a delay which is acceptable for us? And, well, you should always think about the domain. So what actually is an anomaly in a clickstream? How you should describe it when you realize that something is and is not an anomaly. So I will try to answer these questions. First of all, our data sets. We invested in a really, really cool technology called Druid.io. Are you familiar with OLAP cubes? Who among you heard about OLAP cubes? Okay, who among you believe that they could be accessed in real time? Thank you, one, as far as I can see. So, generally speaking, nowadays it is possible. You can build OLAP cubes in real time, and Druid platform, Druid.io is an open source platform, it enables this. This is more or less real time. We set ourselves that 15 minutes of a delay before something goes wrong and notifying is fair enough, because we shouldn't notify the engineers that something is going probably going wrong with their system after 1 minute, because it may fix itself and you shouldn't wake up people in the night. So 15 minutes is fair enough. And you should think about the type of a query. What kind of data do you want to analyze? So, I believe that we're all familiar in pseudo-SQL. This is a kind of data that we're going to analyze in our system. So, you're taking simplest count from category and action of what user is doing. For example, if you're searching something in a web page and then you click on the items that you have searched, this is the category, this is the action, and as I said, it is 15 minutes delay because it is being sliced into 15 minutes, right? Because all up cubes and everything that is from the data warehousing is about aggregates. Simply put, you take all the slicing window, right? 15 minutes, and you slice it, and the events that occurred during this 15 minutes is what you're going to analyze. So, oops. It's not working really perfectly well. Okay, so first question for you. This is the type of data that we're going to work with. And it's a question up to you. What can you see that is more or less the domain of this data? Are there any anomalies here? Come on. Nah? There are no anomalies. Okay. I believe that this is an anomaly, the drop of the traffic here and the increase here. But let's think about something else. Do you see any potential problems with this kind of data? From the clickstream, this is the user's activity. Can you compare day to day? Week by week, yes, that's a very good answer. Because if you think that you should compare this day to this day, it's a very bad idea. Because they are totally different. And even the way that this diagram is being shown is a bit different. And there's one more, a little harder to notice issue with this kind of data. Do you have any idea? Okay, very good point. But holidays cannot be seen here, I can tell you. Okay, so last but not least, this is the issue, that people are going asleep and the drop is really fast. This is a fast drop, and when they are awake, it's really increasing. The traffic is increasing, so it's a very rapid growth and rapid losses. So, generally speaking, you should believe that this kind of data, the clickstream, is periodical. Week is probably a period, definitely not a day, but you wouldn't know it if you haven't looked at it. Days might differ really, really a lot, so it's a worst case scenario to look at them. And there's, as I mentioned, there's a big rapid growth and decrease in the traffic. So, we have done some research, because nobody likes coding, right? If there's a library that can do it for us. And we found some solutions. First of all, there's a Twitter library, and it's really, really good. It is proven, but it's really complicated. It's so complicated that we, as a simple engineers, couldn't know how to use it. There are so many parameters to be tuned, to test, that we define that it's a no-go for us because we do not understand it. I asked you, what do you think about this data? Because nowadays there is a lot of new algorithms based on HTM, neural networks and all this kind of stuff, because they try to simulate what your brain believes in, and they are even more complicated. And we tried a bit and proven ourselves that they are not for us because they are too complicated, and we cannot control what are the impact of parameters to what they are doing. So this is the keyword, simple. We believed that we could provide simple solution to this problem that engineer, not data scientist, could understand. So our perfect model should be simple, time aware, because it's a time series data. It should monitor and be able to alert rather in minutes than hours. It's obvious, because if something is wrong and we know it after 6 hours, it's too late. It shouldn't report many false positives, because it's gonna call the engineers who are at their duty and maybe wake them up. Nobody likes that, so we shouldn't do it. And we checked what's the simplest solution. And it's a nice joke about it. You know, a software engineer goes to the CTO and says, hey, math is so cool and statistics. And CTO says, not really. And he says, have you heard about machine learning? It's so cool, it solves multiple problems. Yeah, it's awesome, we should go and try it. But to be honest, machine learning is more or less about statistics and maths. So we decided to go with confidence intervals. You will understand it in a minute, what's that. And by the way, this is the most advanced tool for designing some kind of algorithms and testing them before deploying to some kind of cluster. We really loved it, and I encourage you to think about what you're going to do on a whiteboard rather than in the code, because we tried both ways, and this is faster. So, we drew a few things, and we decided that we would like to see something like that. This is the traffic, the green line. This is some kind of a prediction, and those are the lower and upper bounds, which says that if the traffic drops below the lower bound or above the upper bound, it's an anomaly. It's really intuitive. Who can look at it and understand if it's an anomaly or not? Okay, so it's self-explanatory. So we have started, and we did our first attempt in learning. It's a very nice acronym. We started with R. I'm on a Scala conference, so I will show you in a minute why Scala is better suited for us than R. But to start it, we started with R. And this is our initial results, so that there are obvious anomalies. Cool. This is probably also an anomaly, but these are definitely not, because these are those rapid changes between the night and the day, and the first initial algorithm didn't handle it well. So we overfit it. Typical machine learning problem. We overfit our model, and it didn't go well. So the problem was the rapid change of metric in the day and the night, and it led to overfitting of a trend, because we want to believe that there are some trendings in a data. Like you put an ad, and this ad is really good, so there will be more page views probably from the items that this ad is about. It's called a trend. It's not an anomaly after a while. So we decided to go further with this model, and we've seen that these boundaries that I've introduced are a bit problematic if there are outliers. So you have to get rid of them. And percentiles, for example, 90th percentile or 85th percentile, are great for outliers removal. They flatten the data, okay, I can accept that, but they're really, really good at outliers removal. And we thought, come on, why do we have duplicates of data? If you're working with Kafka, HDFS, and other kind of it, it's obvious that you probably have at least once and using some kind of a tool to dump data from Kafka to HDFS. We were using Camus, which is totally great at having duplicates. It works perfectly as a duplicate producer. So we've also decided that we should develop something ourselves. But it was an issue, and it came out with a model. We learned something new about our data. So, who among you is a data scientist? Who among you know R language? Okay, in our team, it was like that only data scientists know R good. They can understand the code written in R, and typical engineer does not. So we have decided that although R is great for building models and all this stuff, it's not the best way to go for us, because we have to maintain it. We have to create code that will be developed and will last a little longer. And it's also not easy to monitor the process, the application written in R, whereas in Scala it's quite easy because it's a JVM application. And last but not least, it was really hard to maintain our code because we didn't know it that good. So the decision, we have to rewrite this model, sum up all we have learned, and start a new project in Scala. And so And so we did. Sorry, I will not use it anymore. Sorry. Sorry for that. Okay, so this is a simple case class that's an input from this OLAP cubes. As you can see, you've got some timestamp where the data comes from. And as I told you, right, the model is weekly period. So you have to got the day of the week, because it's really important not to compare different. Hour of the day, because at least the hour granularity is what you really want. And a minute of an hour, because you want to analyze in minutes rather than hours. So this is your query granularity. Then you have to have some kind of a dimensions. You remember this category action in SQL? It produces dimensions, right? Category action, those are dimensions. Those are where you aggregate your cube. For example, searches or add clicks. And we have built a model key, which is time aware, trend and correction keys, which are not time aware, because they are bound to the domain. This is very simple because, for example, if you analyze searches, it's important in the context of search and not globally in the context of, for example, ads, because they can be very different. And the observation is the simplest metric. Then we have created a model. It's quite easy because it can be shown here. It's really simple Scala. I wanted to show you that writing models in Scala is also not so difficult as some people think, that R is the only language that enables you writing this kind of a code. And last but not least, we have gone with some simple math, because that's probably the killer feature of our language, that it's got complex math. But sometimes complex math might be very easily developed in Scala. Please look at this EMMA function. Does any of you know what means EMMA in math? Cool, very nice. That's exactly what's this acronym for. And I will show you in a minute why we decided to develop some kind of a math packages like this. But when you look at it, does it really seem like exponential? If you think of it that it's a stream of data and that this recorded value, right, is being overlapped by each event that occurs. So this is the tail, the first 1 minus weight multiplied by Caris mean is a weight, it's a tail, and this one is the current sample, right? So it's quite easy to reason about it if you start thinking in a streaming way in math algorithms. And it's really possible. Exponential mean average. I will show you in a minute after the code. And then you have a trend, because now we've time aware. Now we know that we've got some maths here, and we've got some trending, because the click stream is changing. For example, when there are Christmas, it's a trend. You can simulate the holidays as some kind of a long-lasting trend. But the trend, as we have already shown, could not dominate the model, because it leads to overfitting, and it was the issue with the first starting point. But there's an important problem here. Let's look at it. For example, these are the aggregates metric counts, how it looks in a timeline. And could you see any potential issues with this diagram? Okay, sorry, okay. Yeah, sure. So, the reason why I'm showing you is this. For example, let's believe that this first period, right here, is the learning period. We are learning our model at this kind of data. And then, here's a deployment. The application with new tracker was being deployed, and this is the situation at the moment. Most of the mathematical functions will go and fail because they have been learned something that it's not obvious and not working anymore, right? It's like this, that it occurred, but it's not valid. And this is why EMMA, this exponential mean average, is so cool, because it's working like that. Events that occurred in the past and are old do have some weight, but it is exponentially being smaller and smaller. For example, If the event occurred now, it has big impact, but if the event have occurred 1 week ago, the impact is minimal. It's still in the model, it's been somehow interpreted, but the impact is minimal and we can move forward. So it's not a bad idea to use this EMMA with time series data if you want to forget what you have learned if it's wrong. And if you were to take something away from the streaming algorithms, that's the key point. If you want to stream and perform some machine learning on a stream data, you have to forget. Things that were in the past should be exponentially removed or treated as less important. Okay, so we're almost there. We have created a very simple code that can show you whether you're an anomaly. It's more or less what you have seen on a diagram, right? You've got this value, you compare it with some kind of a bound, lower and upper, and you just simply say if it's below or above it. It's really simple Scala code. But there's one more thing being remembered here. What's in this situation? We have deployed it to production. It was a big success. And then one of our customers developed their new version of the page week by week. So each week they deployed the new version, and people loved their pages and they were clicking and clicking, and our model was, learned something at that point, and then there's a deployment being seen, and everything is an anomaly from that point. It's, you cannot learn anomalies, you cannot treat them good, because if you learn anomalies, there's no model, you have to detect them. So that's the problem, because long-lasting anomalies are probably not an anomalies anymore. Think of it. If you're a human, look at this kind of a diagram. After this deployment, it's normal, right? After some time, it's become a norm. It's typical situation. And if your algorithm is categorizing it as an anomaly, it should stop at some time in point and says that, okay, I was wrong, I'm mistaken, I should relearn and take under consideration that this is something new. And we have come to the idea that it's not symmetrical problem. Gain of the data, situation like here, that you gather from your web pages more traffic is okay. Maybe you even shouldn't wake up someone in the night. But what about the losing of the data? This is crucial. Losing of the data is probably much more important. So the second diagram that shows you is if it's an anomaly shouldn't be symmetrical probably. So we decided that we should go with a probability, with a sign, with different wages, so that you could apply the monitoring and calling you if it's the loss of the traffic, and if it's the gain of the traffic, then you shouldn't do nothing probably, or maybe think about if there are duplicates or something like that. So, as a user, you define where obvious anomaly starts, and why is that? Because if the point that something is an obvious anomaly starts, and it grows in time, after some time, and you as a user think of it of your SLA on the data, it is becoming a norm. And it makes perfect sense. Think of it this way. You are under maintenance of some kind of a web service, and you've got 3 hours to fix problems with the data. So, if you have achieved this top level that you 100% know it's an anomaly, and it's long-lasting for 6 hours, so you haven't fixed it, it has become a norm. It also teaches you that you should treat your data as a first-class citizen because you had an SLA on it for 3 hours, and it wasn't fixed for 6. So sorry, now it's normal situation. It's your problem at this point, and it really helps for the maintaining of services. So here you see a simple fix. As I told you, the algorithm should be smart enough so that after some time of something being long-lasting anomaly, it's not an anomaly anymore, it's a perfect normal situation. And, well, we implemented it this way. It's a typical probability that is it an anomaly with a sign, so that plus means a gain and minus means a loss. Okay, we're deploying it in the way that you're only delivering something like that. It's really also important to go to the production really fast. And that's what Scala gave us. In R, it was really difficult to go to production and deploy something for multiple clients. In Scala, it was really easier because there were some YMLs or other application properties that could be delivered, and the user only puts something like that. For example, how long is the maximum time of anomaly? How many percentage of anomalies in this time should be treated as a long-lasting anomaly? What is the maximum bound of the standard deviation that you are starting to treat as anomaly? What is the maximum point that you believe that is 100% anomaly? And you do not need to provide all of this data, but it can help you reason about your data as a service. And it is also important. Not only the way you communicate with other customers, but also kind of a data that you produce. And if you look at the second part of this screen, well, there's a simple, do you remember this SQL query? Is it similar to what's down there? I believe it's quite self-explanatory. So it's obvious one-to-one mapping from the fact that someone had written the OLAP cube to this kind of application. And it really worked. That's one of the takeaways. So I would like to thank everyone who was involved. There's one guy who's not working with us anymore, but really did a great job at it, and he enabled us to start it. It's Pavel, so thank you. I know he's here. And to be honest, from the point of R and Scala, it's a common belief that building those models should be done in R. They might be deployed, and it might work. But there are problems, and we've been there, like it's really hard to say if your application is performing well or not. It's really hard to try something new because it's not so object-oriented. And generally speaking, developers like object-oriented or functional programming because it's easier to deliver code rather than in R. So it's also a takeaway. And last but not least, the buzz factor is still really important in your project. If you decided to go with some kind of machine learning stuff in language that only few people in a project understands and know, it's a problem. Because if they decide to be ill or to change the company, then it's your problem then. And with JVM applications and JVM languages like Scala, it's not valid anymore. So I highly encourage you, if you want to start some kind of simple building models and you are not afraid of Scala, it's a really nice expressive language. I've shown you very simple code that was taken one-to-one from R language. I believe that it was quite easy to think about it. And there are many advantages that cannot be seen in first. And the only disadvantages of probably Scala compared to R with it, for me, was the fact that it wasn't so simple to draw the charts, right? But we're using Grafana, so if you have some kind of visualization, it's as good as in R. And then it's up to you. So thank you very much.